Section 4.7 discusses optimization. So these are problems where you're trying to find something that gives you the best, the biggest, the brightest, or the smallest, the least, etc. You're trying to optimize some situation to have an extreme value at some point. Now the one that I like to start out with comes from taking a sheet of paper and cutting off a corner. Now the dimensions of our sheet of paper are going to be, we're going to have 14 squares going this way and 18 squares going this way. We're going to cut off a little X by X piece in the corner. So here's what it actually looks like. Now I've cut out one from the corner here, one from the corner here, etc. And when I do that, I can bend that up into the shape of a box. But of course, I don't have to necessarily just cut out one corner. I can cut out, more than one corner. I can cut out 2, 3, or 4. And of course, this probably doesn't show up too well on the video, so let me pass these boxes around. They're going to have different volumes. And the question is, well, what cut gives me the biggest volume? Now, as you approach these things, there's going to be a litany of things that I'm going to look for. So I label them this way. Picture, draw a good picture. Draw and label. What do you think the F part stands for? Function. You've got to have a function of one variable in order to maximize or minimize. The I is your interval. And what you want to do is you want to figure out, well, what's the domain relative to the problem? Not necessarily the domain in general, the domain relative to the problem. And last part is the analysis. That's going to include derivatives, finding maximums and minimums, etc., enough to satisfy the conditions of the problem. So we've already got our picture for the first one, so good on that. Let's work on the function. Now in this problem, what we're trying to do is we're trying to maximize the volume created by this box. And if you look at the boxes that I've been passing around, they certainly don't have the same volume from one versus the next. So you cut out a corner and then you fold it up. We want to find an expression for the volume of this box. So in general terms, how do you find the volume of a box? Yeah, length times width times height. Length times width times height. Now let's call this the width. That's going to be 14, but then you subtract off an x here and subtract off an x here. Overall, what are you subtracting off? You're subtracting off 2x. And then you've got the length here. So the length there, well, that's going to be 18, but then we also have to subtract off an x and an x from both ends, right? So it's going to be 18 minus 2x. That's going to be our length. And then last but not least is the height. What's the height going to equal? Just x. So I can replace this. The problem with this is that there's 3 variables. I can only work with one. You can think of Calc 1 as being calculus first semester. You could also think of Calc 1 as being calculus of one variable. You can't deal with more than one variable until you get to Calc 3, where you start dealing with multivariable calculus. But for right now, we're stuck with just one variable. So instead of V as L times W times H, let me rewrite that as V equals 14 minus 2x times 18 minus 2x times x. And that's nice. That's exactly what I wanted, because that's something that depends just on one variable. In fact, a lot of times what I'll do is I'll write that to kind of express that relationship. This is v of x. It depends on one variable. Now both of these are little parts of the overall problem. When I grade your problem, I look for these elements. I look for the picture, I look for the function, the interval, the analysis. All right, well, let's take a look at the interval, the domain of this function. Now you could look at the domain in one of a couple ways. You could say that, gee, the domain is, negative infinity to infinity, because after all, this is a polynomial function. Polynomials are defined everywhere. Except, think about what x is. X is how much material you're cutting out from one or the other edge. So how far can I cut until I've cut everything off of this direction? Can anyone figure that out? How many squares can I start cutting out before there's nothing left to cut? 7, yeah. Because 7 from the right and 7 from the left, that's going to meet in the middle. You've cut away all 14. So in practical terms, the interval is going to be 0 to 7. Now, not a real big point here, but it is kind of worth a point. Am I going to include these or not? Can you? Yeah, you can't include 7 or 0. You can't cut off nothing, then you wouldn't have anything to fold up into a box. You can't take out 7. That would be a problem. You can see those points on our graph, here and here. So wherever this maximum is, it's somewhere between 0 and 7, and that's our job to find it.
How does the graph go up after?
Well, remember, it's just a polynomial. What you've got is a polynomial that has roots at 0, 9, and 7. So it's just a cubic polynomial, and that's its behavior. But the behavior that interests us is what's going on with the graph right here, in between these things. Now, one of the cool things you can do with Desmos is you can make it figure out some things for you. For instance, I wrote this function as v of x like this. I can do a little table. I can find, say, v of 1. So v of 1, if I cut out a 1 square, then I get 192 as my volume. If I cut out 2 squares, I get 280. 3 squares, 288. 4 squares, 240. And let's do 2 more. 5 squares, 160. And 6 squares is 72. So somewhere, and we don't know where, somewhere between 2 and 4, this is going to have a peak. Does it peak a little bit after 3 or a little bit before 3? Actually, it looks like it peaks before 3. But we're going to use the calculus to find this exact value. That's our goal. So let's do that. Let's see. Now, to be helpful, let me share with you that if you multiplied this thing out, if you multiply v of x, then you can expand that into a different form where it's going to be a little bit easier to differentiate. So x, 14 minus 2x, 18 minus 2x. So I wrote it as 4x cubed minus 64x squared plus 252. All right, great. I want to figure out where this is actually, to find a maximum, I'm going to need to differentiate this and take a look at the derivative. So let's take a look at v prime of x. That's going to be 12x squared minus 128x plus 252. Yeah. That doesn't look terribly fun in terms of figuring out where it's actually equal to 0. Now, if you're stuck on a test and you actually had to find where it was equal to 0, let's see. I think 12 goes into all. No, 12 doesn't quite go into this one, does it? That's a bummer. Because 12 goes into here. You can divide out by, say, 4. I think 4 will work. Because 4 will go into here. 6 won't go into here.
Okay.
You can divide out a 4. But let's be a little bit clever about this. We've got this nice technology available to us. So let me just graph that. Let's do y equals 12x squared. And we know, generally speaking, what this is going to look like. It's going to be a parabola. 12x squared minus 128x plus 252. And what are we looking for here? We're looking for where this graph changes signs. So at about 2.605 and 8.062. So approximately 2.605 or 8.062. We can do a little testing now. Actually, we don't really need to do much in the way of testing. So we got x, and then v of x and v prime, 2.605, 8.062. Let's give ourselves some nice table. We know it's 0 here and here. And in typical fashion of a parabola that faces up, the signs here are positive, negative, positive. Meaning it's increasing, decreasing, increasing. What's that saying about our point here at x equal 2.605? Yeah, local max. Now there's another way that you can establish that this is a local maximum. And that is by looking at the second derivative. So let's apply the second derivative test. So second derivative test. Because you want to make sure that the critical point that you're working with is actually a local maximum and not a local minimum or inflection point. Now, when we're testing to try and find out concavity, what does f double prime greater than 0 tell you? What kind of a shape do we have? Concave up. And then f double prime is less than 0. Likewise, tells us we have concave down. If you test a critical point in the second derivative and it's greater than 0, what kind of a shape does the function have there? Well, it has a concave up shape. And if it has a concave up shape, then what's going to be true about your critical point? That's going to be a minimum. So if C is a critical point, and f double prime of C is greater than 0, then C is a minimum. Minimum or local min. If C double prime or f double prime of C is less than 0, then x equals C is a maximum. Could be a local or absolute. So it gives you a different way to double check that the point that you're hoping for is what you think it is, either a minimum or a maximum. So to apply that one here, Let's take a look at the second derivative. What's v double prime going to equal for us? Someone make me look good. What's v double prime here? 24x minus 128. And if I take a look at v double prime at 2.605, I'm not going to take out a calculator for that. V double prime of 2.605 is going to be 24 times 2.605 minus 128. Whatever it is, it's going to be less than 0.
Negative 65.48.
All right, negative 65.48. But it's less than 0, therefore 2.605 is a max. So, nice. So you confirm that two different ways. You don't need to do both ways in order to make sure that it's a maximum, but at least do one. Either play around with the first derivative, and formally speaking, this is called the first derivative test. If the function goes from increasing to decreasing, then you've got a local max. Decreasing to increasing, you've got a local min. That's the first derivative test. Sometimes the second derivative test is a little bit easier. It kind of depends on you and the work that you're doing, but whatever works, that's fine. Kata, question? Okay. Nice, nice. Let's keep going. Comments or thoughts on this one before I move on to example B? All right, let's move on to example B. It says find the value that minimizes the distance between the two curves. So let's move on to that one. And I think I've got that demonstrated right here. So here's our two curves. We've got f of x equals x squared plus 1. G of x is x minus x squared. So you got a parabola that faces up and faces down. So the question is, what value of x makes this distance the smallest? So you can move this around. You can see that, okay, whatever value of x makes this the smallest, it's certainly not to the left of this point, nor to the right of this one. So somewhere in here, you're getting the smallest value. Now you can kind of play around with this graph a little bit and watch this distance here. And you can see you can get it pretty close. But to try and find the exact value of x that makes that equal to 0, or excuse me, not equal to 0, that makes that distance a minimum, we're going to have to use some calculus. So let's play around with that. Example B. So we've got f of x is x squared plus 1. G of x is what? X minus x squared? Yes, thank you. X minus x squared. So graphically speaking, we've got two parabolas that face away from each other. You've got a parabola that opens up, and then another one that opens down. And somewhere in between, we want to minimize this distance. What's the minimum distance between these two? So what value of x does that? Well, that's our picture part. Let's work on the function. How am I going to calculate the distance between those two? Well, that's just the distance between the y coordinates, which is these two expressions. So I'll call it d equals f of x minus g of x, our top function minus our bottom function, which is x squared plus 1 minus x squared. Be careful to put that second term in parentheses because you've got to distribute the negative. which is going to give me x squared plus 1 minus x plus x squared. Let's add these two terms together. 2x squared minus x plus 1. And let me call this d of x. I'm calling it d of x because it just depends on that one variable. It just depends on x. Picture, function. What comes next? Interval. Now, is there any natural restriction on this one like there was the last one? The last one, you could only cut so much material off of your box before there's nothing left to cut. So last one we had between 0 and 7. But is there any natural restriction here? No. So your interval is really negative infinity to infinity. It's everything. The importance for your interval is you don't want to be looking for critical points outside of your domain. Notice in the last one, we didn't play around with this one at all because that's outside our domain. We didn't have to. So do pay attention to your interval, please. Last but not least, the analysis. If all you've got is a hammer, then everything looks like a nail.
Derivative.
Yep, derivative. Thank you. Our only hammer right now is the derivative. So let's take the derivative, d prime of x, 4x minus 1, and I want to know where that's 0. Okay, that should be pretty easy. Where does this equal 0? 1/4. Now, I could set up a little table and test values on either side, but let's see if we can't use our second derivative test to prove that this is actually a minimum point. And how would we do that? Well, first of all, I would want to find the second derivative. So second derivative test. So what's the second derivative going to be? D double prime of x equals 4. So in particular then, let's look at d double prime of 1/4. D double prime of 1/4 is, well, it's still 4, isn't it, right? And the important thing is that that's greater than 0. What's that telling me about my critical value here?
Local min.
It's a local min. Yeah, it's local. In fact, actually, in this case, it's a global min. So, therefore, x equals 1/4 is a min, and it's absolute min, I suppose. Absolute min by the second derivative test.
Would the analysis be with therefore technically, or do you want all the work
You know,
for analysis?
the analysis is really just this part right here, finding the derivative and setting it equals 0, finding your critical point, and then I guess the other part is showing that that critical point is actually a minimum.
So on an exam, you'd want us to write out that x equals 1/4 is the min?
It'd make me really happy, yeah, to see that this is a minimum and that you've looked at it with the first derivative test or the second derivative test. Nothing wrong with using the first derivative test. Let's do that down here, just for comparisons. So the first derivative test, derivative. So for the first derivative, we've got, let's see, x, d, and d prime. We had 1/4 was where it was actually equal to 0. Now if I pick a point to the left of 1/4, maybe 0's to the left of 1/4, what's going to happen if I put in a 0 here?
-1.
I get -1. Basically, I get something negative. Something to the right of it, like 2, 8 minus 1. All right, well, that's going to be positive. So it's decreasing, then increasing. So therefore, by the first derivative test, x equals 1/4 is a minimum. Nice. So you can either use the first derivative test or the second derivative test. Doesn't matter. But certainly you'll make me very happy either way if you use either test. I'm very happy to see that. Holly? Something not looking right there? No? Is it okay? All right. Arm? All right, cool. Anything else on example B here?
Is it absolute minimum and global minimum mean the same thing, correct?
Yeah, absolute
Okay.
minimum, global minimum. Yeah, I apologize. I think I mentioned it the other day that I use them interchangeably. It's just habit from years. But I think they go with absolute minimum is probably the more relevant term as far as the book is concerned. Okay. Let's take a look at example C. Want to try and find a point on the graph of y equals sine of x so that this point, the point 4,2, has a minimum distance to the sine curve. All right, so what's all that looking like? Well, I'm glad you asked. Right here we go. So here's the point 4,2. And what I want to do is I want to find a place on this curve so that the distance between these two things is the same, or is the minimum, I should say. So, wow, you can go a lot of places, but where are you going to find that minimum value? If you look, I've got this function here which I called q of s, and yeah, it looks like it's getting pretty small around here. Colder, 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 all right, warmer, warmer, looking pretty good. So somewhere around here, we want to find the coordinates of that point. So let's see if we can't do that. Let's follow along with our favorite 4 steps there. So this is example C. I'm just going to draw a little bit of the picture. So that much. And I'm going to add a little bit to this. Let's call this x and y. And not a whole lot going on there. There's our picture. We want to minimize this distance. And for reasons that I'll explain in a little bit, I'll call that q of x. That's what we're trying to minimize. We're trying to minimize that function. Okay. Picture. What comes after picture? Function. All right. Now the function is going to be the distance between these 2 points. Now let me remind you of the distance formula. So the distance formula, I need either. Distance between 2 points, say x1, y1, and x2, y2. Does anyone remember that formula?
x1 minus y, or x2 minus x1. That.
Yeah, that. Well said. Well said. Thank you. So you got x2 minus x1 squared plus y2 minus y1 squared. And yeah, differentiating this thing looks less than exciting. So there's a little trick that I can show you that'll work here. Minimizing the distance will also be equivalent to minimizing the distance squared. So call that d squared. If I square both sides, what's going to happen to the square root? What's going to happen to the right-hand side if I square both sides of this relationship? Square root goes away. And I think I'd much rather differentiate this then differentiate the other one. Now, we got to still work with this. Because remember, we needed a function of one variable. We don't have that yet. John, let's start putting in some stuff here into this function. What do you think I could put in for starters? All right, 4 and 2. Those are a constant. So it's going to be x2 minus 4 squared plus y2 minus 2, and that's also going to be squared. I still haven't gotten down to the point where I've got just one function. Now, I guess at the same time, we could have also put in an x and a y. So we'll call it d squared x minus 4 squared plus y minus 2 squared, etc. But that still doesn't have just one variable. What could I do to get down to just one variable? Well, here's where you got to look at your problem and think about what kind of substitutions you can make here. This equation is really y equals sine of x. So y and sine of x are interchangeable. So I'll rewrite this as x minus 4 squared plus sine of x minus 2 squared. Oh, okay. Now I can replace that with q of x. And the reason I replace it with q of x is because if you try to differentiate, d by dx of d squared, it just gets a little messy with all the d's. So I just gave it a different name, that's all. All right, so picture, function. Whew, a lot of work to get that function. What next? Mage? What after picture and function? Some help? Ethan? Interval. Thank you. Interval. Is there any natural restriction on x? Do I have to say, all right, well, we're just going to cut off x here, or could x be anything?
Anything past 0?
It really could be kind of anything. Now, I did kind of cut it off a little bit because you can see that this is getting bigger and bigger and bigger, but there's no really restriction to the left, and there's no real restriction to the right. But you can see the sweet spot is probably somewhere around here. But there's really no restriction that is coming to mind. Now, we will kind of play around or dance around the fact that I don't think we're going to be able to solve this analytically. But that's all right. The interval is negative infinity to infinity. And finally down to the analysis. Give yourself a second, try and differentiate that. See what you get.
So it says d squared. Do we still have to square something at the...
No, I just relabeled d squared as q of x. So what I'm going to do is find q prime of x. So yeah, I didn't want to deal with the d by d squared of
like,
d dx.
Like the squared and d squared, it's just to get rid of that square root. That's all
Yeah,
we
we squared that relationship to get rid of the square root. That makes it easier to differentiate and easier to work with this function.
Just wanted to make sure it didn't change anything to like...
It's not going to change the minimum value. It does change the function we're differentiating, but that's a good thing. That's why we did it. This is kind of unique. This is the only trick that I know of relative to the problems you're going to see where this actually works. Generally speaking, you're just going to have to derive your function, and that's it. Keegan, what are we going to get for the derivative? What's q prime of x going to look like? Okay, fair enough. Pause here. Okay. How are we doing? Okay? All right. Let's start here. You have to use the chain rule, right? Derivative of the outside, 2 times x minus 4 to the first power. What's the derivative of the inside? Just 1. So derivative of the inside doesn't come into play too much here. Keegan, how about this one? What's going to happen when I differentiate that one?
2 parentheses sine x minus 2 times cos x.
Yeah, times the cosine of x. Nice. And we want to figure out where that thing is equal to 0. Now, I don't think we're going to be able to solve this like we could factoring a polynomial, solving just a regular trigonometric equation. So we're going to use a little technology here to help us out. But are we okay with our derivative there?
Why don't you expand the x minus 4 into like x squared minus 8x?
The derivative would still be the same.
Oh, okay.
If you think about x squared minus 8x plus 16, when you differentiate the constant, it'll go away. Differentiate an x squared, you'll get a 2x. Differentiate the minus 8x, you get a minus 8. So this is just the factored form
Got it.
of this when you expand it. So you can,
Which is
you know, just
longer.
it does feel a little bit longer. Not that much, not oppressively. Okay, so what we're going to want to know is, well, where does that derivative equal 0? Kind of a cool thing you can do with Desmos is you can graph like the derivative. So if I do y equals q prime of x, and I can get the graph there, and yay. Let's shut off this other graph real quick and look for where the graph has minimum or has points across the x-axis. Going from negative to positive, what's happening with the derivative there? Or what's happening with the function? The function is decreasing and then increasing, so that could be a minimum point. You could have a minimum point over here. But looking at the graph of our original function, if I shut these things off, then it looks like around 2.6, that's going to be our minimum point. You can confirm that with the first derivative test or the second derivative test. Let's just get that value again. This is something we can solve with Newton's method. That's section 4.8. So that value equals about 2.651. Yeah, it's 2.561 or 6512. All right, so that's our minimum point. Let's just take a look at it, trying to plug it into our function. So if I make this value 2.5 or 6512, let's see, turn that one back on and shut this one off. There we go. There's your minimum point. This function, this distance, doesn't get any smaller than it does right here. If I move this to the left or to the right, notice that that number, that distance squared, gets bigger. So, beautiful. All right, I'm going to pass on the first and second derivative tests here, just in the interest of time. I want to do one more example, and then we'll take a break.
Quick question for you.
Yes, please.
With the interval section, could we use like just general knowledge that sine, like we know where the sine graph is, so like we know it's going to be between pi or half pi to pi.
It is reasonable to say, all right, I know it's not going to be past this point or this point. Mathematically, that feels a little sketchy because a lot of times things can be misleading in terms of what they look like. And I don't, let's see, I I do have an example of something like that where the picture is completely misleading. And it looks like you manufacture something out of nothing, but
So we got
I can't,
catfish.
I can't put my hands on that right at this second. It's kind of cool though. Let me see if I can just Google it. Missing triangle or missing square in triangle puzzle. Yeah, here we go. Right here.
Oh,
This one. This one bothered me no end in college. And when I was a graduate student in math, I looked at that and I literally cut out, you know, these shapes out of a piece of paper after I printed it off, and I couldn't figure out, well, why is this piece missing? They look the same. You count the shapes, you look at the shapes, they look the same. So picture proofs don't always work. It's really frustrating. But there was, I mean, the subtlety that's going wrong. Katie, you want to spill the beans? Okay.
I was going to ask if it was, but it looks like you're pointing at it.
Yeah, if you take a look, this is not a straight line. The slope of this line and the slope of this line is different. And when you rearrange things, that's how you manufacture that seemingly missing spot. But it's really subtle. So pictures can be misleading, which is why we prove things, so that you don't get catfished. All right. Nice question. Appreciate that. And I hope that the answer is a little bit satisfying. All right. Let's continue with example D, and then we'll take a little break after that, kind of an in-class break. Let's see. No, not that one. Here we go. So one of the cool things that I can do with Desmos is something for you that I couldn't do until Desmos, and I had to rely on just kind of your imagination afterwards. So for example, D, we've got 250 feet of fence, and we're going to enclose a rectangular pasture near the edge of a river. So, all right, that's great. Likely speaking, if you had all this fence, you probably want to give your herd as much room to roam as possible, so you want to try and maximize the area. Great, let's do that. So the picture looks a little bit like this. But what dimensions maximize the area? Do you want it tall and skinny? Do you want it wide and short? What works best? So that's a good question. What's the happy medium? Do you want it really wide and very narrow, or very short, or tall, narrow? Where's the happy medium? If you keep an eye on this A of C here, then somewhere in between you can see that, all right, 7,800, yeah, 78-ish, 7812. So somewhere around there looks like the best that you're going to get. All right, but what's the actual best? So let's see if we can't figure that out. Let's draw ourselves a picture to start with. And all I know is that I've got 250 feet of fence to work with. That's not a lot. Now this is the river part of it, so okay, got a river there. My fence is really these three sides. What can I label? This is going to be what you're going to face, so think about it for a moment now. How can I label this? What should I label with what?
Length 1, length 2, length 3.
Length 1, length 2, length 3? Okay, I can do that. X, Y, and Z.
Just length 2.
Ah, length 1. All right, so let's label this X, and then what does this have to be?
X.
And then this could be Y. That's our picture. Hope you enjoyed it. Let's take a break. No, I'm kidding. Well, let's finish this one up. That's our picture. That's not really all that dramatic. Let's head towards the function. Now the function is really going to be the area of this, right? So how do you find the area of this rectangle? X times y. Thank you. Let's keep going. There's a problem with x times y. What's the problem with x times y as far as we're concerned in this class?
Two variables.
It's got two variables. We need it down to one variable. There's something we haven't used yet. What information about this problem have we not used yet?
50 for the area.
Not 250 for the area, but 250 for
Length,
the length.
so it would be,
X.
and then y minus x, or x minus 250.
Close. The length of this is x plus y, or better yet, 250 equals 2x plus y.
So x, or 2x equals 250 minus y.
I think I'd solve for y there, because it's just easier.
Yeah.
So 250 minus 2x, and that's what we're looking for. This is the kind of thing that you're going to have to do time and time again, is you're going to have to play around with this to make this a function of one variable. I can't emphasize that part enough. You have to make this a function of one variable. So a, then let's see, of x is going to be x times 250 minus 2x. Great. So spinning that around, that's going to be negative 2x squared plus 250x. Wonderful. Laura, what now?
We define the interval.
Yeah, interval. Now let's think about it. Does it make sense for us to use negative numbers here?
No.
Can we have 0 for x? No.
No.
So that's on one end. Is 0 going to get a parenthesis or a bracket?
Fence,
Parenthesis. Yeah, you can't have 0 as a height for this fence. How about the other end? What's the maximum?
250.
Not quite.
Oh. 120.
Because at 250, if I did 250, that's enough for one x, but then I have two of them.
125.
Yeah. So half of this, if I use 250 for this fence and 250 for this one, that gives me nothing for the width. So really, excuse me, if I use 125 here and 125 here, I've got nothing left for y. So 125 parenthesis. Great. Finally, the analysis part. That's going to be the easy part in this. The first derivative is going to be minus 2x plus 250. How about minus 4x? My bad. I said this was the easy part. So there's the first derivative. I want to know where that's equal to 0. So set that equal to 0. I'll move the 4x to the other side. 250 equals 4x. So 62.5 equals x. And that matches very nicely with what we saw when we were looking at our diagram, right? That it was very close to, it's very close to 62 is where we were getting the maximum. All right. You can double check that with the first derivative. So if you did the first derivative test, a prime 62.5, then at 62.5 you get a 0. To the left of that, the function's increasing. To the right of that, the function's decreasing. So this is a maximum. 62.5. Yay. Comments or thoughts on example D here? All right. I'm going to split this up into two parts and make it a little bit easier on the viewers. So we'll stop things here.